Hey, what's up guys, my name is Cherno and welcome to episode 3 of the Genesis series, a series of videos in which we look at one of my first ever games, in fact my first Ludum Dare game, and we just take a look at all the stuff that was wrong with it, all the stuff that was right with it. We'll kind of just talk about it and we'll see if we can fix any of the issues or rewrite any of the particularly bad codes. So anyway, last time we talked about a whole bunch of classes that existed in the actual game. It was mainly stuff like input, and I don't even think we talked, we talked about the level, about the menus and all that stuff. But today I promised we would talk about graphics and rendering, and then next episode, if we don't have time this episode, which I don't think we will, because as you know, I like to talk, next episode we will talk about like the game logic and how all that stuff worked. So I know that's like quite a few videos, because I think this is episode 3, right? Episode 4. So it's like the first 4 videos are going to be like just talking about the game, and then I guess the remaining like however many videos will just be kind of fixing it and actually doing stuff, I guess. So I'm not 100% sure what we're gonna do with that, but anyway, looks like we'll just kind of take this as it is. I'm actually using a different microphone as well this time, so let me know what you think about the sound quality. I mean, it should sound really good because it's a really high-end microphone that I used back in the music studio. So anyway, but I thought I'd actually take it out and record a video with it because I do love the way it sounds. Okay, so anyway, all that aside, let's begin. So we will probably take a look at, like, well, I guess we'll begin from the beginning, right? I mean, we did cover kind of Cherno color last time, but the big things that are in this graphics thing are, let me just mute my phone. The big things that are in this graphics package, right, which I'm assuming is going to contain all the graphics, is map, screen, sprite, and sprite shade. So we'll kind of begin from map, I guess. Again, remember, I have no idea how any of this works. Oh, I know what this is. No, we don't need to cover this at all. This actually wasn't in the original Ludum Dare game. This was something that I started adding afterwards. This is something that I started adding on afterwards when I decided to have like a little mini map in the game. In fact, I think you can actually bring that up. I think there's something. Where would this be called from? Control-Shift-G, I think. Nope. Reference nowhere, really? That's probably a lie. Let's see. Yeah, here it is. Map render. It's commented out. So if we uncomment that. All right. If we uncomment it, yeah, you can see that we have this map here, and when I hit play or whatever, let's find the good level. Yeah, you can see that we have a mini map which shows females as red dots, and then I guess children as green dots, and you can see the 2 females spawned here. So it's good for like both debugging, but also like I thought I might have it as a mechanic. I don't know, just because it's obviously a lot easier to play. It's kind of like cheating if you have the map, because you know exactly where everyone is. It's actually more pink than red, but anyway. You can see that as I collide with this, like another mob will spawn, right? And you can see that by that mini-map. Anyway, so I know a lot of you are probably going to ask a little bit about how that works. It's really simple. In fact, the way I did it back then was a bit weird, but essentially we have the width, height, and the scale of the mini-map. So I did scale it up by 2, just so that those pixels would be even bigger and you could actually see them. And then all I literally did was I went through all of the entities. So this render method, of course, was being called from the game class. Excuse me, hang on. All right, I'm done. So all the rendering kind of happens from the render method in the main class, in the game class. So yeah, so it was the last thing that we rendered, and then we just called map.render. We passed in both the graphics context and the level. We cleared this buffered image that we created especially for the map. We cleared it to black, right, with this line. And then we essentially just went ahead and let's see what we did here. Okay. Yeah, so we essentially just went through all of the level entities. We divided their position by, I don't know why I wrote it that way, but anyway, we divided their position by 16 to convert it from like tiles into pixels, I guess, or from pixels into tiles. And then I guess we assumed that the map was 128 by 128 or something like that, because that was also coincidentally the size of the image. And then, of course, we essentially just okay, so we even checked to see if we could spawn a child and we change the color of the female according to that. And then of course, if it was a player, then we set the color to white. Otherwise, for all other entities, so like for the children and stuff, we set the color to this, which you can see is quite high on the green. So that's why you see it as a green kind of pixel. And then we drew the image, okay, at a specific scale as well. Okay, and that's pretty much it. So it was really easy. Like we essentially just drew pixels onto our bitmap based on where entities were. So that's the map class. Nothing too fancy. It wasn't in the original Ludum Dare submission, so I don't really want to cover that in any more detail than I just did. But I think that should be enough detail anyway. All right, the screen class is where all the fun stuff happens. Because the screen class actually contains, I believe, most of the rendering code. Yep. So what we have, in case you guys are not familiar with this rendering setup, which you should be because I'm assuming a lot of you have watched the game programming series, but if you haven't, it's pretty simple. Basically, essentially what we do is we set up a buffered image, right, which is just essentially like a texture. Think of it as a texture because that's kind of what it is. With a certain width and height, obviously, and with a data type, right, or a pixel kind of format. And then what we do here with this line, and it's a bit confusing because this stuff all kind of happens, sorry, microphone. This all kind of happens statically in the sense that like, you can see it happens in the initialization of the class. It's not done in the constructor. Probably should move that down. But anyway, this line will happen first, right? And then essentially we'll get the pixels, which is basically obtaining the rasterization kind of data buffer from the buffered image, right? And then extracting its data, which will essentially, well, we'll get the data buffer. We'll convert it into a data buffer int. We know it's an int because we've set the format to an int. And then once we have the data buffer int, which is a Java class, we want to actually get the integer array, the primitive integer array, which is what we do via get data. And that's how we get the int pixels. So that is basically how that works. Now, a few things. This is essentially our color buffer, right? If you're familiar with kind of GPU rendering and all that stuff, this is what you would call a color buffer, right? This is basically the buffer that will essentially be blitted onto the screen when the buffers are swapped, okay? That is the entire, this pixels array, which, by the way, just so you know, right, this is an array, right? So in Java, arrays are passed by reference, which means that what we're actually obtaining is a reference to this array. Yeah, this isn't like some other array that we've created or something, because a lot of people I remember, like way from the game programming days, way back from the game programming days, were like, how is us changing this pixels? How does that affect the image at all? Well, all we're doing here, remember, is we're not like creating some other new integer array. We're just obtaining a reference to the integer array which makes up this image. Okay, we're just taking that reference. So whenever we modify these pixels, it's actually modifying the pixels that make up this image. And so because of that, we can just do stuff like, well, we can just write into our pixels array and then draw the image, and it will essentially draw that pixels array. Okay, so that's how all of that works. So because of that, and this is an interesting way, it's basically, well, it's software rendering. It's never going to be fast because what we're doing is, well, apart from writing into an integer array and stuff, we're essentially kind of, we're losing any kind of hardware acceleration because we're dealing pixel per pixel. The only hardware acceleration that would ever be possibly done is drawing that final kind of image. But again, it's Java. I don't know what it's doing behind the scenes. It's probably really slow as well. So it's not a great way to render, obviously, but it is really nice for pixel games because you do literally get everything pixel per pixel. You do get full control. You can theoretically do anything with this. Like, it's not going to be particularly fast, but if you wanted to render 3D stuff, you could totally do that. Anything that you could do in like a pixel shader or a fragment shader, if you were using OpenGL or DirectX, you could do with this, obviously, because you have the entire array of pixels. You can just, you know, have a for loop that goes through all of them and then write your shader in there, and there you have a fragment shader or a pixel shader. So anything is possible with this, right? It's just that it's going to be really slow. So I, of course, nowadays wouldn't really recommend doing that. It is still, I would honestly still write games like this if the deal, like if the goal was like a retro kind of pixel game that was like, you know, kind of Game Boy era-esque, right? Something that was really low res, like, you know, I mean, this is kind of high res even, but something that was like, I don't know, what, well, like a Game Boy resolution was like 160 by 9, like it was 160 by 120 or something. I don't know, it was really low, right? Like something low resolution that you can then scale up at the end, this is totally perfect for, and you will get good performance out of it. I mean, the game programming series, I think, runs at like 2000 FPS, right? And that's scaled up a little bit. Like 3 or 4 times, I think. But anyway, the point is, this is an interesting way of kind of rendering. I was going to, like, way back, I was going to make a series just dedicated to, like, covering this style of rendering and what you can do with it. Because again, a lot of people don't understand that you can actually do some really cool lighting effects, and you can do all this cool stuff with it because, well, you've got full control over it, which is really cool. So I don't know if you guys would be interested in that, and that's just something that that I remember I wanted to do like 2 years ago, but never had the time to. So there's a lot of really cool stuff we could do with this. But anyway, that being said, what we do is we create the screen class, which the screen class is essentially just a class that is dedicated to manipulating this pixels array. Yeah, that's really all it is. We can basically we can pass the screen around all of our kind of, it's like our rendering content. It's essentially our renderer. Right? We pass the screen class around all of our classes that we want to be able to render, like, you know, mobs, for example, and like, you know, level, I guess, well, yeah, the level's going to have to render its tiles and stuff like that. And then all it has to do is say stuff like, hey, screen, I want you to render a rectangle, or I want to draw a texture here, or I want to, you know, draw text or something. That's the whole idea. I don't think we actually support text, but that is something that you can do, okay? So that's the screen. So we create it with a width and height. You can see what we do here is we have a public in pixels. So this is a bit weird. This is something I personally don't like, which I will probably make a note of because we can fix this really easily and it would probably boost the performance a lot. Is what I actually do is I actually maintain my own pixels array in here, which is again a bit weird. Because you can see that what I'm doing is I'm creating a completely new pixels array, which is the exact same size as our screen, okay? And again, this would make sense if we had like multiple screens or something, but we don't. So what I'm doing is, again, width and height, of course, is the width and height of our game pre-scaling, because we only scale it at the end when we actually like blend it onto our final kind of buffer, onto our screen buffer. But we have the screen, we create a new pixels array for that, and then we do all of our rendering to this pixels array. And so what happens at the end, which is again not great in this case, is we have this lovely line of code where we go through every pixel and we copy it from, we essentially copy that screen pixels array into our pixels array so that we can draw it. That's not going to be too good for performance. I mean, like, theoretically it shouldn't be that slow, but this is like Java we're talking about, so I think that actually will be quite a little bit of performance drain. I'm just curious real quick, like if I were to get rid of that. So what are we at, 500 FPS? Yeah, see, just that whole thing is like 150 FPS. Now obviously we can't like play like this screen's never going to change. But you can see it's quite a bit faster, right? If we're not doing that copy, which is a bit, like, it shouldn't really be taking that much time, but it is. So getting rid of that is fairly simple. We can just pass a reference of our pixels array to this screen class. In fact, I might do that right now, just like, well, we might do this formally later, but I'm just because it's such an easy and trivial thing to do. I just want to see how much faster it'll be, because this is all we need to do. And now we can basically we don't need this anymore. And it will still work as it should, right? And so what is that, like, I mean, it's like 600 FPS, which is more than we had before. So it's quite a bit faster, because we're just avoiding that copy. Yeah, so anyway, that's something that we can do. I mean, I've just done that change now. I said this would just be an exploratory kind of episode, but it's just such a simple change. So anyway, so that's how it used to work, right? It used to create its own pixels array and then kind of write stuff onto that. And then we used to copy it back onto our pixels array in the game class so that we could draw it. And remember, this pixels array is actually the pixels array from this image, from the buffered image. Whereas this is just an integer array. Okay, so anyway, we have our screen class. We set up everything here. We have a clear method, which essentially will just set every pixel in the array to 0. So it'll basically just do a mem set like to 0 for all of the pixels. The 0, of course, is black, especially in a 24-bit kind of RGB kind of format. So essentially, we're just clearing the screen to black whenever we call clear, which I imagine will be at the beginning of the frame. Yep, here it is. Okay. We also have this screen.graphics G, which is interesting. So as soon as we create as soon as we obtain the draw graphics, which is essentially the graphics context, we immediately pass it into the screen class, so that the screen class now has access to this G thing, which I'm assuming we use for stuff. Yeah, we use it for text rendering, okay, because I didn't want to write my own kind of text rendering, which is fair enough. I mean, it's going to be that's not something you want to do during Ludum Dare. So we have, anyway, moving on though. We'll get to the text rendering later. So we have render tile. So this, I'm assuming, gets called from like all the kind of level classes, and essentially it will just draw a tile. We'll draw essentially a texture. So what we do here, first of all, is we have this X offset and Y offset. Again, something that is interesting, like, because it's not typically something you would want to store in a screen class, I imagine, because this has nothing to do with the renderer and everything to do with the level. But essentially, X offset and Y offset would be the level offsets. So we use this set offset method, which gets called from the level render class, right, at the very beginning. And it basically just sets our offset to our screen kind of scroll, right, which is calculated from the player, I imagine. Yes, so we have the X scroll and Y scroll that are being passed into level.render, and it happens over here. So it's just player X minus screen width divided by 2, so we send to the player essentially. Okay, that's all we're doing. So this X scroll and Y scroll is essentially going to be the offset of the world based on the player's location. That's all it is. And so we of course need to do that so that when we move the player and the camera moves, essentially it's a camera system, right? When the camera moves, the tiles essentially have to get translated somewhere. In both the X and the Y axis. So that's what happens here, and that's why we have this offset. So if we request a tile to be rendered at 0, 0, because it's the top left tile or something, but the player has moved the camera, right? Then of course we need to translate that tile's location from 0, 0 to wherever it actually is based on the camera's position. So that's how that whole system works. It's pretty simple. There's nothing really too complicated about it. It's just a simple offset. But it does the job, and it's pretty simple. I just probably wouldn't do it in here. Like, I would probably, if I was writing this code to be better, and if I cared. See, a lot of these things, I just feel I have to mention this. A lot of these things are not done because I was necessarily a bad programmer back then. I mean, some of them certainly were done because I was a bad programmer back then. But a lot of these were just done because, like, it was by far the simplest way to do it, and there's no real downside. Like, doing it this way, there is no real downside. I mean, technically, it doesn't really make too much sense, and it would probably limit how versatile this class is, but we're not writing a game engine here, right? We're writing a game for a 48-hour game programming competition, right? And I think this game was about 20 hours of work from me, and that's including stuff like music. So, like, actual programming is probably like 15 hours or so. So it's really not that. Like, it's hard to be like, it's hard to criticize my code too harshly in some cases. Of course, in other cases, that criticism is needed. But in some cases, such as this, it's like, well, yes, it's not that correct, but it kind of is in the context of this game and this competition. So I don't know. Again, I'm going to try and criticize this code as if it was something that a studio produced after like a year development cycle or something. Because, well, maybe not that much, but you know, I'm going to obviously try and treat this as if it wasn't created in a 48-hour game programming competition, because, you know, I could use that excuse everywhere. Like, oh yeah, but it was easier to do it this way. Or I had an idea, but then I changed my mind, so this is the code that's left over from that. You know what I mean? Like, there's so many things that could happen. So I'm going to pretend that this wasn't, I guess, for Ludum Dare. But anyway, in that case, if this wasn't for Ludum Dare, then yes, I definitely wouldn't have this here. I would probably have this offset in the level class, and when you go to render it, that's when you actually pass in the positions already offset into this as parameters, right? So you would do this calculation outside of the rendering thing. You would do this back in the level class. Okay, cool. Anyway, and you'll probably even have a camera class, and you could even have something like a camera.apply translation or something like that, and you'd pass in two numbers and you would get two numbers back that have the transform applied to it. So in fact, that would probably be even better, right? Delegating all that work to a camera class. This does not contain a camera class as far as I'm concerned, no. Okay, and I wouldn't think it would either. Because again, a camera is a construct that you make when you're trying to do things properly, not when you're trying to make a game in a short amount of time. Okay, anyway. Okay, here we do rendering. So we have the for each loops here, or the for loops that go through both all the x and y. Tiles are of course square, which is why we have the size repeated twice here. See, one thing that I do like that I did do back then is I always wrote my I always wrote out my for loops in kind of the x being the inner loop and the y being the outer loop, okay? And that's really important because if you switch these two around like that, right, that's actually going to result in completely different performance, right? It's going to be a lot worse. And the reason is that if you decide to read an array in memory, and I'm not going to dwell too much on this, but if you decide to read an array in memory, you know, kind of y first, then you're actually kind of skipping. You know, I mean, if tile does sprite to size is like, I don't know, I think this is like 16 or something. I think it would be probably loaded in. Yeah, but there'd be 16 by 16, right? Essentially, if you were reading it down instead of across, then you would be skipping, you'd be reading like multiples of 16 as indices, right? So you're skipping all of those pixels and you're kind of jumping across a whole bunch of pixels at once, right? You're not reading in a row. Which is terrible because essentially you're going to result in CPU cache misses all the time, right? Because what happens, and again, I'm not really going to give you a lesson about this right now, but just to summarize, when you request, you know, data from memory from your with your CPU, it prefetches a lot more than you request, right? If you request like an integer, it's not going to give you an integer. It's going to return you like a whole bunch of data that is starting at that integer address and going forward. So what happens is if you decide to read data that is directly adjacent to or next to your original memory address that you're reading, which would be like one of these pixels, for example, if you read the next pixel, then that's already going to be on your CPU cache. And because of that, that memory read is going to be 1,000 times faster, right? Probably more like 100 times faster. But anyway, it's going to be a lot faster, right? And so if you decide to not do that, if you decide to read your array like all over the place, like you would be if this for loop was inversed, right? Then you're basically throwing away all the stuff that's on your CPU cache. I mean, this is very small though. It is 16 by 16, so it's not a huge, if it was like 1024 by 1024, then you would definitely see a huge decrease in performance. But even something like that, though, is a really good habit to get into, to just write your for loops properly, which is like this. I mean, I've never written them any other way, because the way that I first saw them written was like this, which is correct. But I do see some people write the 4x part first and then the 4y, which is just completely wrong, right? So yeah, so anyway, so to stay on your CPU cache, you want to be reading stuff like this, right? You want to try and read memory that is closer together rather than further apart. That is your ultimate goal. Okay, cool. So anyway, one other thing I want to quickly mention regarding memory and performance and stuff like that is a lot of people always ask me why I don't use two-dimensional arrays, because two-dimensional arrays in some cases to some people make more sense because of course a level is 2D, this is a 2D game, so why are the pixels not 2D? The reason I don't use two-dimensional arrays is because, again, they have the kind of the same problem in terms of how the memory is laid out. A two-dimensional array is essentially an array of arrays, right? So you have an array of pointers which point to other arrays. And those arrays are going to be in various locations in memory. So when you decide to read certain pixels from a certain array, it's almost, you're essentially adding another indirection, right? You have to hit a memory read to obtain a pointer to the address of an array that is somewhere else in memory. Like, it's absolutely terrible. And your performance is just going to tank really hard. So I don't use two-dimensional arrays because they're terrible, like they're pretty bad for performance, especially like for rendering, right? Because we're hitting them so often. We're hitting these things like hundreds of times per frame, right? It's crazy. Probably even thousands. But also, not just because of performance, also I just find it neater to just have this. I mean, you know, having your x coordinate plus your y coordinate times your width is just, I mean, I'm just used to it, and I think this looks fine, as opposed to something like this, which you would probably have typically in an inverse order as well. So you'd have like, you know, that essentially, right? I honestly prefer this. It just makes more sense to me. Okay, so that's a little explanation of two-dimensional arrays and why I'm not using them particularly. But yes, the primary reason would be performance, but also because I don't like them. I mean, I do use them sometimes, just not for like performance critical code like rendering. You wouldn't find many two-dimensional arrays being used in rendering, I think, anywhere. Okay, so anyway, getting along with this, I'm going to drink some water because I've been talking for a while. See, this is what I mean. This video's going to go on forever. It's been like 25 minutes. And before you know it, I'm going to say I've got stuff to do with my life and leave again. So we don't want that to happen. So let's just get on with this. So we go through tiles, which is square. We get the xt. So what is the xt? Y plus yp. Okay, right. So this is the position of the tile. Okay, I see. This is the position of the tile on the screen, right? So we basically get the position of the tile in the level. We translate it to the position of the tile on the screen, right? So we get it in screens, in this xp and yp after this offset is in screen space now. And then what we do is we essentially create a new variable called yt, which is the actual pixel that we're dealing with. So it's of course the offset of where it is on the screen plus the value of this y in our for loop, right? So it's the actual pixel coordinate. So whilst this stuff is per tile, this stuff is now per pixel, xt and yt. We do a little if check here to see whether or not, wow, that is some interesting code. Okay, so we check to see whether or not essentially our pixel is in the bounds of our screen, right? So that we basically clip it to the screen. But the thing that there are two things here that are weird. Right? The first one is this xt is less than minus tile.sprite.size, right? So less than -16. First of all, -16 or anything between -16 and -1 inclusive is not a valid place for a pixel to be. So it will result in an array index out of bounds exception and crash, right? But furthermore, not to mention that, we've also got this directly under it, which just sets it to 0 anyway, right? So that is a little bit interesting. I mean, I can see what it's doing. I can kind of see what it's doing since we do have a break here. So what it is doing is it's saying that if it's like, you know, anything below -16, we'll just quit out completely. But if it is between -16 and -1, right, then we will clip it. Well, we won't clip it. We'll set it to 0, right? Which is, again, extremely weird. And we do that for y as well. So, and the other thing, the second thing that's weird is we have this break, right? Which will just, you know, abort rendering that entire tile. Whereas what we probably should do is continue. Break will definitely give you high performance because again, we just abandon that tile. Which again is why we have this negative tile size, I imagine. If we had this as 0, in fact, we'll test this out right now. But if we had this as 0, we'll be losing a bunch of tiles because again, we're breaking. So let's see what this looks like. That actually seems to work, surprisingly. Oh, no, here we go. Whoops. See these black areas? There we go. I'm surprised that it's not happening up here, but anyway, all these black areas are a result of that whole thing. So what we really should have done is just hit continue. And if we do continue, you can see we don't get those black things because we only skip rendering certain pixels rather than the entire tile if one pixel is out of bounds. And then we also don't need the need for this anymore. So that would be kind of fixing that up. That will potentially result in reduced performance though, because we are rendering pixels that we weren't before, but I don't think it will since we were just clipping them to 0 anyway. So that's an updated way to do that. That is a lot better. I'm not sure what I was thinking exactly. I think I was just, oh, and you know what that will do as well? That will fix that weird bug that we had. Remember how in the first episode I said that like this was being clipped or something? Yeah. You can see that tree, you can see we have this line here, right? If I change this to be that, then, okay, well those are the trees anyway, so that's not gonna, we need to change that in the tree code. But essentially that will be why, right? It'll be because of that, because we're setting it to 0 if it's out of bounds, essentially. All right. So back to this. So then we get the color, right? And we obtain that by looking up our sprite at x plus y times sprite.size. Now x and y, of course, is this for loop that is in between 0 and 15, right, inclusive, because that will be, you know, this sprite size will be 16, right? So we're going through that. So basically x and y are always going to be a coordinate of our sprite in terms of pixels. And then we have, and then we're of course multiplying it by the sprite width, which is the sprite size because it's square. So multiplying it by 16 so that we can get the appropriate coordinate in the array. And that gives us the sprite's color. So what we have now is an if check that basically checks to see if the color is pink or purple. And if it's either pink or purple, sorry, if it's not pink or purple. So if it's either pink or purple, then we don't render the pixel, essentially. We don't render the pixel. However, if we also do another check here to see if the tile is not an instance of torch tile. So if the tile that we're rendering is not a torch, then we apply our color change to it, our brightness change, based on level brightness. So this line is us applying lighting to the actual pixel, based on the level's kind of brightness. So this is not lighting, so to speak, like as in this isn't the torch light or whatever. It's not what you see from the torch light. This is just the natural light. Yeah, that's a good way of saying it, I think. Natural light, in terms of this is just the light of the level, right? Without lights applied. So because of course we have a day-night cycle, the level will get darker because the natural light will kind of decrease and then it will increase again. So that's what this is doing. It's changing the brightness, which of course is just essentially reducing the brightness of each color channel, right? And that's what we're setting color to. So we're passing in the original color and we're getting back the color with the brightness applied to it. Okay? And I apologize for any noise outside. There seems to be like people just mowing lawns and stuff. But anyway, so this is what we do here. And we don't do that if it's a torch tile, because I assume we want the torch tile to remain the same bright. Like essentially we just want the torch tile to remain the same brightness. Regardless of the regardless of natural light, because it's always going to be emitting light is basically the concern there. Okay, cool. And then we have our final kind of line here, which is the most important line of the function probably, which actually sets our pixels, which is what we see on the screen eventually, to that color. Okay. Now, of course, this can be, I do say that this is what we see on the screen eventually, but of course this can be overwritten before we do render it, because we can render stuff on top of things. So that may not actually be on the final kind of thing, but it will be. This hair, man. Oh, sorry, I gotta get my hair under control. You'll see me do that quite often throughout the video. Anyway, so that's us finally rendering that. And that is how we render tiles, okay? It's pretty simple. There is an almost identical render tile method here that actually should not exist, but does anyway. I mean, I guess it's a little bit different. The other thing different about this, well, apart from the fact that it takes in a sprite rather than a tile, of course, is that we don't do the check for the torch tile, right? So even if we decide to render a torch tile with this, it will apply brightness to it. Now, there are a few things that are obviously wrong about this whole thing, right? And I mentioned the first thing was this. Also, stuff like having, hey, if this isn't a torch tile, right in our renderer is very bad. But it's also something, again, that is like, yeah, but it's Ludum there, and this is obviously a specific renderer for this specific game. So it's not something that is particularly evil in this case. 30, oh my goodness. Man, these videos take up so much time. I don't understand. Has it really been like over half an hour? What have I been doing? I need to watch some of I think I need to watch some of these back and see what I actually do during the time. Because like we're halfway through like essentially the first like graphics class. Anyway. You guys wanted in-depth videos from me. Here you go. This is pretty deep. But anyway, this could obviously be like, it does have that one small change, which I doubt does anything. So this whole thing could just be rewritten as render tile XP YP. I just screwed that up, didn't I? I meant to do it the other way around. So you could kind of rewrite this whole thing as render tile Excuse me. And tile.sprite, right? You could just do that. Now that, of course, in this case would render torches incorrectly because we don't have that magical check to see if the tile is an instance of a torch, but you guys kind of get the idea. I probably could have done something like that. And we can't do that if check in here, unfortunately, because we don't know the tile at that point. We only have the sprite. But yeah, so stuff like that could be rewritten to be a bit better. You can see this still has that dodgy piece of code, which I will fix on the fly. Okay, random mob. Wow, this is some exciting code. So we have a few parameters here. We've got an integer called flip and a boolean called hurt, which we don't actually use. I imagine that I like, you can't really hurt. See, this is what I love about looking through old kind of source code. You get to see stuff that, like, stuff that was kind of in development but didn't make it to the final game. Like, there is nothing in this game currently that will hurt you, right? But why is there a hurt variable, right? It kind of gets, the plot thickens, right? It kind of gets exciting. So I believe I did initially start to add enemies, but I didn't have time. So essentially what that hurt thing was I guess a boolean whether or not that mob was taking damage, and if so, I probably would have like made the color tinted red or something, right? In fact, that's probably where that color tint could have been used as well. Or maybe I just would have made the mob flash white or flash red or something, right? So I'm guessing. I don't remember at all what that was for. But anyway, so we have this. We do the offset, of course, the camera offset. Now here we don't even bother with using variables like sprite.size. That stuff is lame, right? We're pro, so we just use 16. So that's fun. Of course, that is the sprite size. We then get the pixel, and then we get this ys, which is called y, which is just equal to y for now, okay? And I'm assuming that ties in with the flipping. Yes. So flips, right? How do we flip sprites? So flipping, first of all, is something that we use to essentially, like, literally flip a sprite, right? So we essentially scale it like negative 100% by either x or y, or rather either vertically or horizontally, or both, right? We can do both as well. I imagine most of it's probably horizontal though, because if the mob is moving left versus right, we don't want to have two different sprites. We can just mirror them. So that's what the flipping does, first of all. So obviously, flipping, there are kind of there are four states of flipping: 0, 1, 2, and 3. And this is me all obviously just taking this from the source code. We have 0, which is no flip. We have 1, which is just an X flip. We have 2, which is just a Y flip, and we have 3, which is both an X and a Y flip, which is why we have this. So that being said, all we have to do is essentially just reverse the order in which we kind of read pixels, right? So you can see that we read pixels using XS and YS, but what we do here is instead of like kind of reading pixels 0, 1, 2, 3, 4, 5, etc., we instead do 15, 14, 13, 12, 10, 11, right? We read it in reverse order. That's all we do, right? That's all the flip does. It's literally a flip in the order that we read pixels. And of course, by reading pixels this way, right? Reading pixels right to left, but obviously, you know, setting them in the color buffer as left to right, we end up with a flipped image. So that's how flipping works. Then we have this comedy code once again, which I will be fixing. You can see here we have negative 15 and negative 16 here. Okay, that again is interesting why we have 15 here and 16 here and not 16 in both or 15 in both. Weird. But anyway, that's gone. And just to check it was still XT. Yep. Okay. Then we have, of course, the color, which we take from the mob sprites pixels. We check to see if the color is not pink or purple. And then what we do here is, okay, so if, oh yes, this is great. This is the good code. So if the mob that we're drawing is a female, and the female can spawn a child, and the current pixel's color is this, which is kind of a red color. Yeah, very red kind of color. Then we set the color to green. Okay, so this is that tag that you see on females. I really need to disable the other levels. Where is a female? Find me a female. All right. So this tag that you see on females, see this green kind of thing, right? That is of course, that shows whether or not they can spawn children or not, right? So basically what we do is if they can spawn children, then we set this tag to be green, okay? Which is this color. If they can't spawn children, then we don't run this if statement, so we don't change the color at all. So that would mean that in the original sprite sheet, that color was actually red originally. So let me just confirm that. So this is resources or sprites, of course, is what I want. Yeah, I love the fact that my Windows 10 is broken and doesn't like have photo viewer or something. But yeah, so you can see that originally it's red, okay? And that red, of course, you can see is BC2823, which is BC2823. So if the color is equal to that, then we change the color of only those pixels. You can see that this like color doesn't exist anywhere else on the female, right? Only here. So this solid color, if we're about to render a pixel that is of that color, then we will change the color to be essentially this color, which will be this kind of green. And you can see that, you can confirm that by just pasting this in. There you go, there's that green color, okay? So that's how that works. It's pretty simple. It's just a really simple case of changing a color on the fly if it is a certain color to begin with. Okay, so if the color is less than 0, so if the color would be less than 0, wow, the color should never be less than 0. Oh, no, it will be here. Wait, this is very odd. It's weird. Okay, this whole thing is a bit weird because the color should never be less than 0 because we are rendering a 24-bit. Yes, we're rendering a 24-bit color, essentially, just RGB, right? And if we have a 32-bit integers in Java are signed, and we have a 32-bit signed integer, which means that the color can only ever be negative if we are using more than 31 bits, so to speak, right? So if the color is higher than 2 billion, for example, it kind of will spill over into negativity. So essentially, if we have something that begins with FF, then yes, that will be negative if you convert it into a signed integer because that requires unsigned, right? Because it's that big. So that being said, this now will be kind of a negative number, probably. However, our final render doesn't need that extra channel, so I'm not sure why we didn't just do something like that. I mean, fair enough, reading that original color from the mob, it would probably be read in, like Java would read, like, because I think the way that we read this stuff inside Sprite, probably, Sprite sheet, yeah, we read it just as a buffered image, so this will probably read the image format of the actual image that was exported, which apparently was 32-bit RGBA, which is why we have this extra channel. That's why we need this when we check, and not just that, right? Because it does have that alpha channel that we need to also check for, otherwise the numbers, of course, are not equal. And yeah, so we could have just done that, but we didn't. We've just set it to that. And then we see if the color is less than 0. And if it is, that's actually incredibly weird. I'm not sure what that code exactly is trying to do. Okay, whatever. Anyway, so and then we apply lighting to the mob, I guess. So this is important code because we're gonna have to fix this eventually. But we changed the brightness of the color based on the level, of course. And this, by the way, will return a 32. The changed brightness returns a 24-bit color anyway. You can see it has no alpha channel, so that's even weirder. Like, we seem to have a discrepancy here between having an alpha channel and not having an alpha channel, which is not good. I probably didn't know what that was back then, so. I mean, I would have, because I wrote stuff like this, right? So I probably just didn't think of it. And then we have this. So basically, if the mob light distance is less than 0. Oh, okay, right. So if the mob's Okay, so if the mob's distance from the light is less than 0, then we just apply the regular level brightness. Otherwise, we basically multiply the brightness of... yeah, so based on how far away the mob is from the light, we will basically... make them brighter if they're close to the light. That's what that will do. But I guess that the light distance will get set to -1 or something if the mob is a certain distance away from a torch. Or something like that. What are we at? 45 minutes. It's time to wrap this up. We're going to finish this class and then we're going to be done for today. Okay, cool. And then we have the pixels, of course, which sets this up. This color less than 0. I don't get it at all. Color will, as far as I can see, color will always be less than 0. Unless I'm very wrong. Let's remove this and see what happens. Because I honestly don't quite know whether or not, like I don't quite see that happening. So I guess we'll see it when... I guess we'll see it if... Yeah. So we should see that applied to both. I just don't... So that's also saying that we'll only change the brightness if the color is less than 0. It's so weird. That is very weird. If anyone can remember what on earth I was smoking when I wrote this code. This should always be true, as far as I can tell, because whatever we read, oh man, yeah, this has to always be true. There is no way this isn't always true, now that I think about it. Because the most significant bit is always going to be 1, since it's set to F, and it's always going to be set to F, because even though this is a 32-bit color, the alpha is always going to be full. Which means that the 32nd bit is always going to be 1, which means that the number is always going to be negative, because it's getting cast into a signed integer. Yeah, so that distance you can see with the light that makes it darker sometimes, but it also doesn't work half the time. Or is dodgy. That is because of that. Yeah, I don't know. This code shouldn't be here. I don't think that matters. Maybe there was something, maybe that's a result of me trying to do something in the past and then changing my mind or something, but it doesn't make any sense right now. Because as long as there are 32-bit colors, which there will always will be in this case. I mean, it's hard-coded to always have to have a 32-bit color, otherwise the game just won't look correct. It'll always be like that. I mean, it seems to work. I don't know. That's... I need to take a look at that. Okay, render light. Again, we do the... I don't know what this does at all. So it looks like we take in a tile and RGB and intensity. So we do our normal code with this crazy stuff. We do XS, which is just equal to X. Okay, we don't even need that, right? This could just be X, I guess. And then we have color, which is again from the tile sprite. Where is this called from? Render light. From light tile. Okay, cool. Interesting. We should look at light tile. We'll look at lighting. Okay, since we're already past the time limit, we're going to look at the light rendering stuff next time. Exclusively the light rendering stuff, including the light tile class and all of this stuff. But to wrap this up, we have our set offset function, which is really easy, of course. It just sets up our offset. Sets our offset fields to the parameters. And then we have render text. So render text will basically render us text with a certain color. Again, I don't know why I did this. Because I believe there is a constructor, at least now there is, maybe there wasn't back in the day, but there is a constructor that just takes in a color. I could have just done that. Okay, other stuff that is bad is me creating a new font every time Don't want to do that at all because that's going to be slow. I'm imagining that it's going to have to like create a new texture and then fill it with like glyphs, which is not good unless Java has some internal kind of caching stuff. I don't know if we would be able to see that. As in we would be able to see that, but I don't know if Java would have actually done that because it is Java and you know they're not really that good. Okay, so yeah, this dot style, sure. Okay, that's constructor. So it doesn't look like they have any kind of cache. I'm not going to spend too much time looking at this right now. I'm just seeing if there's anything here that... Surely they have to have a cache though, come on. There's no way that they wouldn't have a cache. That's the stupidest thing ever. I'm just going to assume they have a cache because fonts should always have caches. Create font. Yeah, they've got to have a font. That's from a font file. Okay, whatever. I'm not going to look at this now, but I'm assuming they have a cache because that would be madness if they didn't. Okay, anyways, but still, creating this font is bad news. Don't do that. Again, I'm not sure if... Oh, no. What if the reason that my font rendering on the menu was so slow was because it used this code and this didn't have a cache? No. Oh, that's nuts. Well, that's fun. I hope you guys learned something because next time I'm going to add a cache and see what happens. This is on my to-do, okay? I'm going to leave to-do. So we're going to cache that. And that's my biggest to-do, really. I mean, we've already done our to-do, which was... I'll still leave the to-dos there, I think. Oh, no, well, I mean, the thing that we did do this time was fixing up our pixels here, right? And not doing that. But apart from that, yeah, next time... Or at some point, probably not next time, but we will definitely cache this and see what happens because I'm predicting it's just going to be a lot faster. In fact, it almost definitely will be a lot faster. Okay, cool. Anyway, and then of course the way that we render a font here is in this case we extract a bunch of colors, which we didn't need to because this constructor takes in color anyway. It might be it might want a 32-bit color. No, this is RGB, yeah. But it might want like a 32-bit color and not a 24-bit color. But anyway. Whatever, I'm sure it could figure out the fact that the alpha channel is 0 or something. But anyway, then we have a font we create. It's always going to be Verdana though. And then we set the color of the graphics context, right? So we do text rendering on the fly, meaning that there is no kind of submission, there's no queue. We just render it, like as soon as you call render text, it will draw it onto the buffer, 100%. So G set color to whatever color we just created from these RGB values that we specified using this integer color, which is here. Using the font that we just create every time here, and then we draw the string at the given X and Y, okay? And this, of course, will be used primarily by the menu, I imagine, but by everything, really. I mean, we render stuff like click to focus, we render stuff like the population display, right? We render the timer, and then we render, of course, all of the menus, which is a lot of stuff to render. Okay, so we use that quite heavily. The thing that's important to remember there though is that it should, like, text will always be written over top of other stuff, right? Because in our main rendering order, we draw our image first, right? And then we do stuff like, yeah, so we render our level stuff, then we draw our image, and then after that we would be rendering all of our other stuff, like our menus and stuff. Yeah, menu.render, you can see it happens here, population.render happens here, because of course this image takes up the entire, oh, sorry, microphone. This image takes up the entire screen buffer, and it's not transparent or anything at all, and it's the entire screen. So we have to render the text in front of it, otherwise we won't see the text at all. But yeah, okay, cool. Anyway, and then we don't have this stuff after as well. And then the timer. Okay, so that is it. That is the screen class. Next time we're going to talk about lighting, and then after that we're going to talk about game logic and stuff. But anyway, I hope you guys enjoyed this video. If you did, please hit the like button, and I'll see you guys next time. Goodbye. Vroom.